Hello, this is a project overview from Team 13's warehouse bot built during the spring 2024 semester at Clemson University for Electrical and Computer Engineering Senior Design 2, or ECE 4960. Members of the team include Connor Harris, Kevin Burke, Robert Lunn, Brody Woodard, Thomas Indoni Chirizzi, and Boyd Thomas. Together, we worked towards building a car capable of lifting small boxes for transport. Our motivation for this project was the need to improve warehouse or assembly line worker convenience, enforce one-piece flow in the work environment, ensure safer transportation of the product to the workstation from the pickup point. In the scenario depicted below, a member of a warehouse or plant works on small, lightweight components like electronic boards that require testing. The pickup area for these box components is unfortunately not beside the workstation, so the employee must step away from their station to grab a component each time it is needed. Alternatively, the employee could pick up multiple boxes, but this increases the risk of dropping fragile components and could disrupt one-piece flow. With a fully automated and obstacle-avoiding warehouse bot, these components could be brought to the operator without them having to leave their station every time a new component is needed. Our objectives for the warehouse bot include building our own frame within a 300mm by 250mm area, allowing some parts of the car to branch off, perform 0-degree turns and side-to-side movement, integrate a vertical and pinch system on the car, lift a 1-pound box, have everything run on a 12-volt 6-amp-hour battery, perform obstacle avoidance, adjust pinch to the box size, communication with the car through a wireless controller and web server, and lastly automate the car for pickup and drop off. Unfortunately, we were not able to complete the obstacle avoidance, box size adjustment for the pinch system, and automation for the pickup and drop off before the end of the semester.
Moving on to project implementation, this is a picture of our finished product. To start off, we have the frame of the car, which was designed using aluminum extrusion. On top of that, we have 3D modeled mounting platforms that hold the various components used throughout the car, like the motor drivers, the FPGA, and the power rails. We also have a compartment for the battery at the front of the car. And then on the rear of the car, we can see the vertical lift and pinch system that is used to squeeze and pick up the box using a 3D printed rack and pinion. Moving on to the mechanical review, we have 3 main systems, which are the frame, the vertical system, and the pinch system. Again, the frame is built using aluminum extrusion, which in this case is 250 millimeters wide by 300 millimeters long. This frame sits on top of 4 mecanum wheels, which allows us omnidirectional movement. And we also have an aluminum extrusion vertical guide for the lift system. For the 3D prints for the frame, we have motor mounts, the battery compartment, electronic mounts, and the linear actuator mount. Moving on to the vertical system, we use 2 12-volt 64 Newton linear actuators. And for 3D prints for this system, we have the printed vertical guides as well as the linear actuator mount and stabilizers. For the pinch system, we use a 5-volt servo motor to control the rack and pinion, and steel slide rails to allow the squeezing. And again, we have the aluminum extrusion arms for the pinching. For 3D prints for this system, we have the rack and pinion itself, along with the mount to the rest of the car, and the padded foam grip to allow better friction when picking up the box.
So now I'm going to go into an overview of our electronics. We used 2 linear actuators, 4 DC motors with encoders, a servo motor, and the associated motor drivers with those. On top of that, we used an IMU, an inertial measurement unit, and an ESP8266 for our web server communication. All this was tied into our Butterstick FPGA, which was also running a RISC-V softcore. Wiring, we had a few different voltages that we had to work with. We had 12 volts, 5 volt, 3.3 volt. For all our power wires, we used 22 wire gauge, and our signal wires were 24 wire gauge. We had our dedicated power rails as well for all this, and you can see the wiring diagram below.
The programming for this project was split into two parts, firmware and software. Firmware ran directly on the car while software ran on a laptop external to the car. The firmware included a real-time operating system that was ported to RISC-V for this project, an ESP8266 driver and UDP server, PID loops to control the speeds of the motors, and tasks to read in the orientation from an IMU. The software included a web server that was written in Go and a controller script. The controller script was written in Python and allowed a user to use a DualShock 4 controller to control the car remotely. The controller was able to control the car thanks to a protocol written on top of UDP. This protocol had a packet ID which was used to distinguish between different types of packets. One such packet was the controller packet. This included information about the controller state, such as the axes on the analog stick. The car would then take this information and determine how it should rotate and move. Buttons were also sent inside of a bit field. This was used to determine if the pincher should go up or down, or open or close.
The web user interface was designed using HTML and CSS. It uses post method form submissions to transmit button press signals to control the bot whenever secondary manual input is required. It is hosted on a laptop locally using Golang and continues the previous task until the stop button is pressed. I've included a screenshot of the user interface at the bottom left. As you can see, it is very simple and is only able to carry out the most basic tasks. It can move the robot forward, backwards, left, right, in the diagonals, turn it to the right, turn it to the left, move the fork up and down, and open and close the arms. I've also included a screenshot of the Golang segment that reads the button presses and sends it to the car via UDP. The web server uses a protocol on top of UDP to describe to the car what the last button pressed was, similarly to what we did with the controller. However, instead of constantly polling the web server to see what the current state is, since we're using buttons, the last button will control the direction of the car until a stop button is pressed. The rotate, up, down, and open close buttons, however, work the exact same way that they do on the controller. A bit field is sent at the end of the packet to tell the car what task to do when the button is pressed. Unlike the directional and rotate buttons, the up and down and open close buttons do not require the stop button to be pressed afterwards. Since the car can only move the arms up to the top, down to the bottom, and only open them to the extent of the bar and close them to the extent of the bar, it will not move further than what is required.
Overall, our design was a success. We were able to build a car that is capable of driving, picking up boxes, and moving them to a new location. Throughout the process of building the car, we ran into problems such as our pinching system not being able to lift the boxes, and our linear actuators not being strong enough to lift the weight of the vertical mount. In the end, we were able to overcome these issues by using a rack and pinion for the pinching system and replacing the linear actuators with stronger ones. A few strong points of our project are that we designed our car from the ground up. We also used an FPGA and had mechanism wheels which allowed for omnidirectional movement. Some of our weaknesses were that we were unable to make our car autonomous during the time frame of the project. We were unable to lift more than 1 pound off the ground with our vertical system. And lastly, the mechanism wheels occasionally fell off the DC motor after long periods of driving.
In the future, we'd like to add autonomous driving capabilities. To achieve this, we'd fully integrate the LiDAR system with our FPGA and utilize SLAM to map a room. After mapping, a user would be able to specify drop-off and pick-up locations anywhere in the mapped area via the GUI on the web server. Thanks for watching. Bye-bye.